morning, everyone. I'm Dr. Tripti Mittal. The topic of my presentation is method of least squares. Today, I'm going to tell you about method of least squares, where we can use it and how we can use it. What are the applications of method of least squares? So here are the outlines of my PPT. We will first introduce introduction about this topic. Then we will find what is the procedure and how we can use it by forming the normal equations for two method of least squares. Here is the introduction part, why we are going to use it, and introduction how it is defined. Basically, method of least squares is used to find the best fit for a given set of values. Suppose we have set of pairs, say x and y, from x1, y1 to x and yn, and we want to find the exact relationship between these two variables. With the help of forming an equation to the curve, we can find the exact relationship between these two variables. This procedure is known as curve fitting, and this curve fitting can be found out by the method of least square principles or principle of least squares. In various books, this is known as principle of least squares, and we call it also as method of least squares. We can also find this best fit to the curve by graphical method or the method of movements. But now we are going to discuss only method of least square for this slide. Basically, curve fitting is very important in both theoretical as well as practical point of views. In theory, it is useful to study in the study of correlation and regression. We can find equations for correlation and regression lines, and we can find the relationship between two variables by simple algebraic expressions, say polynomial, exponential, or logarithmic functions, which we are going to do in the further slides. We can also estimate the unknown variable when we have the known values of the corresponding variable with the help of this method. So, first of all, we will study what is method of least squares, how we can apply it, what are its prospects. Basically, method of least squares provides unique set of values, the constants, and which describes a best fit to the data. We can find a best fit of the curve with the help of finding the value of the constants with this method of least square. We will discuss later on what do you mean by this least square. But first of all, we will study what are the prospects we are taking in this method. That is, we have suppose m paired of observations, say x1, y1 to xm, ym for two variables, say x and y, which we need to fit in the given polynomial of degree n, which I have represented by equation number 1. That is y equal to a plus bx plus cx square plus up to kxn. Now, if m is equal to n, then we get a set of values which will satisfy this given system of equation. But what if m is greater than n? Then there will be no such solution to satisfy all these m equations. For this to find, we need introduce some constants for which we will find the values which will satisfy all these equations. So this how method of least square principle exists or started. Now, to find the value of these constants, we will put the values of x, say by considering them as x1, x2 up to xm in this given equation number 1. On putting the values of x1, x2 up to xm in equation, we will get set of solutions for which we have denoted it as y1 dash, y2 dash up to ym dash, where this y1 dash, y2 dash and ym dash are the expected values corresponding to these given set of values, say x1, x2 up to xm. You can see that we have m set of solutions now from y1 dash to ym dash. These are what we have expected. These are my expected values. Now, it must have some original values or observed values. We all know that when we take the difference between observed value and expected value, that is denoted by error. And we expect that that error should be least, it should be minimum, so that we can get the best fit to the curve. Now, what if we take the square of this error? This value will become much less. So that's why this method is known as method of least square. That means we are considering the errors, and after that we are taking its squares. Now, on taking all such errors from equation y1 dash to ym dash, we will take the sum of all these errors. This is why we call it as method of least square. Now we are going to do this procedure only. For this, we have introduced a new quantity, say u. E is denoted for error, that is the difference between observed and expected value. When we take the square of all these errors and add them up, we are denoting it by a quantity, say u. I'm denoting it by capital U. Now we have to choose the value of the constant such that the sum of squares is minimum, that is u should be minimum. No, the condition for u should be maximum or minimum is that the partial derivatives of all the constants involving in the equation, that is a, b, c up to k, these must be equal to 0. So on solving the equations, we get few equations which we are denoting it by normal equations. So how you will do? We have this equation. On putting the values, we will get some values. On putting the observed value, that is yr, and expected value yr dash, and taking the partial derivative, say del u by del a equal to 0, then we will get one equation like this. On taking another partial derivative, that is del u by del b, equating it to 0, we will get another normal equation represented by this, and so on. If we keep on proceeding like this, we will get these equations. These all set of equations are known as normal equations, and on solving these equations simultaneously, we can get the values of the constants a, b, c up to k which we have introduced, and they are n plus 1 in number. Now there is one more important remark about this method of least squares. That is, this method does not help us to choose the degree of the curve. We cannot decide the degree of the curve by this method, which is needed to be fitted in what we have in the given data. But we can find the value of the constants when the particular curve is given to me. If I have a straight line, I can find the values. If I suppose polynomial curve of degree 2, degree 3, degree 4, we can find. If the particular curve is given, then we can find the value of the constants, but we cannot decide the degree. Now, first, we will see that how we can fit a straight line to the given set of values. So here, the same concept. Suppose now instead of the polynomial that we have studied earlier, this is a polynomial of degree 1. I'm considering a polynomial function of degree 1, say y equal to a plus bx, and I'm denoting it by equation number 2. Now, this is a straight line which I need to fit in the given set of values from xi, yi, from where I is from 1 to n. Now, as I discussed earlier, the error is basically the set, that is the difference between the observed value and the expected value. So, this is my observed value yi, and this is my expected value f of xi. Basically, we are denoting f of x as a plus bx. So yi will remain as it, and instead of f of xi, I am replacing this value a plus bx, that is minus a minus b of xi. So this is my error. Now, according to the method of least squares, we will take the square of this error and take the whole sum for this. We are denoting it by a quantity, say u, that is summation of ei ka whole square. Now, u will become summation of yi minus a minus of bxi का whole square. This is my ui. Let us mark it as equation number 3. Now, according to the method of least square or principle of least square, this u should be minimum. For it should be minimum, since we have two constants over here, a and b. So that means partial derivative of u with respect to a should be 0 and partial derivative of u with respect to b should be 0. We equated these two partial derivatives equal to 0. So let us partially differentiate it with respect to a first. What you will get? This will be twice summation of yi minus a minus b of xi into minus 1. We are equating it to 0. So on equating it to 0, I will get equation like this. So this is my first equation when we put del u by del a equal to 0. That is twice summation I equal to 1 to n yi minus a minus bxi minus 1 equal to 0. On solving it, now we can expand it. To solve it means we need to expand it. That is summation of yi from y1 to n minus of this summation of a means what? When I is 1 to a, so that will be n of a. Then b will taken out from the summation and summation of xi. This we are going to equate it to 0. So on solving it, we will get summation y equal to na plus b summation of x. This is my first normal equation for straight line. Similarly, on equating del u by del b equal to 0, we will get our second normal equation. Now, partially differentiate this equation number 3 with respect to b. What you will get? That is same twice summation of yi minus a minus bxi whole square. Now I will get extra term, that is minus of xi, and I will equate it to 0. So similarly, when we take or open this summation, what we will get? We will get summation of y. Then for this, I will get summation of a means here we will multiply first, that is summation of x is also there. So that's why we are getting a summation x plus b summation of x square. So this is my x will also come here. So this is my second normal equation for the system of for straight line, for fitting the data to the straight line. Now on solving, we from the given set of values, we can find the value of summation y, summation x, summation of xy, summation of x square, and on putting the values in these two equations and solving them simultaneously, we can find the values of a and b. Now on finding and then equating them, on putting the values of a and b in the equation y equal to a plus bx, will get a best fit to the straight line. So this is how we apply the system method of least squares for fitting a straight line. Similarly, we can use method of least squares to fit various data for polynomial function of degree 2. That is, we can get a polynomial function, say y equal to a plus bx plus cx square. We can find the normal equations by all these substitutions, that is by finding the error, then equating del u by del a equal to 0, del u by del b equal to 0, and del u by del c equal to 0. We will get three normal equations for this second degree polynomial, that is summation of y equal to na plus b summation x plus c summation x square, then summation xy equal to a summation x plus b summation x square plus c summation x cube And third equation will be summation of x square y equal to a summation x square plus b summation x cube plus c summation x to the power 4. Like this, we can fit a second degree polynomial also. Similarly, you can find further more function curves like this. In the next slide, we will discuss few questions, how we can fit a straight line to the given data, and we will discuss few other functions also like exponential logarithmic functions. So these are the references from which you can consider, that is B.V. Ramanna, B.S. Grewal, and Edwin Krzyk. Thank you.